In this video, we're going to be discussing how Le Chatelier's principle applies to solubility equilibria. So once again, I want to start off with a couple examples because this really isn't anything new, just kind of throwing new terminology on it, looking at this in a new context. So working with the same equilibrium system as the last video, the first question is asking you if you add lead chloride to a 0.1 molar sodium chloride solution instead of water, would you expect the equilibrium concentration of lead 2 plus to be higher, lower, or the same as in water? And then to actually calculate that concentration for that situation. So I would ask you guys to take a couple minutes here and think about this. So think about this in terms of Le Chatelier's principle, that in the last video we talked about adding ionic solutes to water, but in this one we're adding them 2.1 molar sodium chloride instead, remembering that this exists as separate sodium ions and chloride ions in solution, and there are chloride ions involved in this equilibrium. So think about how that would affect the concentration of lead in the system at equilibrium. And then for this one, I would ask you to just set it up, don't solve it. So see if you can set up your ICE table that you would use to do these calculations. And then I'm going to make your life a little bit easier and show you how you can simplify the math on these. So think about this one, set this one up, take a few minutes and do that now. So for this first part, we're looking at the situation where lead chloride is dissolved in a sodium chloride solution instead of in pure water. So there's already a solute present in there before we add the lead chloride. So I mentioned that this is just an application of Le Chatelier's principle, essentially. What we've got going on here is in the last video, we looked at dissolving this in pure water. In pure water, there is no lead, there is no chloride present until you put the lead chloride in there. However, in this situation, we already have some some sodium chloride present, which means we have chloride ions already in there, which is one of our products. So in this case, we're starting out with some product already present at equilibrium, which means our reaction doesn't have as far to go. So this is a little bit different than other Le Chatelier's problems only because we're not starting from a state where we're already at equilibrium, but we are starting with more product already present in our system, specifically Cl minus. Which means we don't have as far to go in order to get to equilibrium. So not as much lead is going to be formed. So we would expect to find a lower concentration of Pb2 plus than we did in water. So this is just applying Le Chatelier's principle to a different type of system. But this type of situation has a name, or this effect has a name. Because we are not producing as much lead, means we are not dissolving as much stuff, our solubility is lower in this situation. So our solubility of an ionic compound didn't leave myself enough space. Is lower when there's what we call a common ion already present in solution. So in this example, the common ion was the chloride. That there was already some chloride present in our solution, and we wanted to dissolve something else containing chloride, in this case, lead chloride. So the solubility of an ionic compound is always lower when there is a common ion already in there. It's just an extension of Le Chatelier's principle, but this idea is known as the common ion effect. We can't dissolve as much lead chloride in this solution because there's already chloride in there, and that chloride concentration affects this equilibrium. If we think about it from a more mathematical standpoint as well, we know our equilibrium expression is essentially the lead concentration times the chloride concentration squared. And those two things multiplied together at equilibrium need to equal the equilibrium constant. So if my chloride concentration gets bigger, my lead concentration has to get smaller. And by already having chloride in the solution, I'm increasing that concentration, which means I can't produce as much, I can't have as much lead present as at equilibrium. So this is known as the common ion effect, and we can also calculate this value exactly using an ice table. We can figure out what that lead concentration will be, or what our molar solubility will be. In this case, those two things are the same, actually, since our lead concentration is just equal to X. So let me just move this onto the next page. Cool. So if we want to actually calculate this value, we still want to recognize that the lead chloride on our reactant side is a solid, so we don't need to think about that column. The one thing that is different in this ice table is that we are not starting with 0 chloride. We are starting with 0.1 molar chloride. Since that's the solvent we're putting this into, before any of our lead chloride dissolves, we already have a 0.1 molar concentration of chloride, even though there's no lead present yet. So since we still have 0 lead, we're still going to have to increase these concentrations to get to equilibrium. And for every X lead we form, we get 2X chloride. And then at equilibrium, we will have generated X molar lead and 0.1 plus 2X molar chloride. So the only thing that changes in the ice table setup is that in water, this is 0, because our initial row in this type of reaction, or this type of equilibrium system, represents whatever our solvent is before our solute has dissolved. Our solute here being, in this example, PbCl2 dissolves. Our change is how much actually dissolves. And our equilibrium is how much stuff is present in our saturated solution. So before we dissolve any lead chloride, we already had 0.1 molar chloride present. So for this example, we will need our equilibrium expression. Once again, we have the concentration of lead times the concentration of chloride squared, since that has the coefficient of 2. Reactant is a solid, so that gets left out. So if we plug in everything we know here, we are given the value for KSP of 1.6 times 10 to the minus fifth. Our lead concentration is X. Our chloride concentration is 0.1 plus 2x, and that gets squared. So if you wanted to do this out exactly, you would end up with a third order polynomial, which is something that is solvable. Your calculator can do it for you. But we can simplify the math on this one. So what we need to recognize in order to be able to simplify here is that the value of K we are given is very small. And this works for all equilibrium problems. This simplification is not unique to solubility in any way. You can apply this anytime K is very small. The cutoff typically is K being on the order of 10 to the minus fifth or smaller is when you can apply this simplification. So because K is very small, that means that this reaction is quite strongly reactant favored. That is what a small value of K tells us, which means that very little product is going to form. If very little product is forming, that means X is also very small. So if X is very small, adding or subtracting X doesn't make a lot of difference, mathematically speaking, to the number of sig figs we have available. So what we can do, based on all of this, is we can ignore added or subtracted X. In this expression. So that means that if we want to simplify our lives, we can say that 0.1 plus 2x, because by all of this logic that we just discussed, we know 2x is going to be a really small number. 0.1 plus 2x is effectively 0.1. So I can say that my value for K, 1.6 times 10 to the minus fifth, is approximately equal to X times 0.1 squared. And just ignore that plus 2x because it's not really going to make much difference. We do have to keep this one. Multiplying by X is going to make a big difference. Multiplying by a very small value changes things a lot. But adding or subtracting a very small value doesn't really change much about anything. So we keep this one, we keep this guy, but we can ignore this one that's just being added to 0.1. Compared to 0.1, X is going to be very small. And this expression is much, much easier to solve, clearly. So from here, we can solve for X really simply. So 0.1 squared is 0.01. So we have 1.6 times 10 to the minus fifth is equal to 0.01 times X. And if we divide both sides by 0.01, we find a value of X of 0.0016 molar, which is equal to our lead concentration and also happens to be equal to our molar solubility. So we found this concentration in water in the previous video was 0.016. In this one, we found 0.0016. So we can see that the concentration decreased by a factor of 10 by the introduction of that chloride ion in the initial solution. So we can see mathematically here that our solubility decreased. So we can see the mathematical effects here of the common ion effect, that our solubility is decreasing because we already had that chloride ion present in the initial solution.